Good day, everyone. Today, I want us to consider VBT and MOT in explaining bonding in coordination metal complexes. And coordination metal complexes are usually formed by transition metals and nothing more. So, just a short recap of what is VBT. VBT uses orbital diagrams to explain bonding. Okay, that's what VBT does. Okay, it uses orbital diagrams to explain bonding. We shall see what are orbital diagrams for those who have forgotten. Whereas molecular orbital theory, or MOT, uses energy level diagrams and orbitals as well, okay, to explain structure and bonding in compounds. Then, after that, we shall use a combination of the two, which we call CFT, to explain CFT is crystal field theory to explain how bonding happens in metal complexes. So, this VBT and MOT were done in structure and bonding, which I assume either you did it in first year, some universities do that in first year, others do it in second or third year. So you have already done this. So this is just an application of what you've already done. Now, let us first of all move to CFT with respect to explaining structure and bonding in metal complex. So our complex of interest is chromium hexaamine ion, which is positively charged. All of us know ammonia. Ammonia is an NH3 with a lone pair, okay? And therefore it is a neutral ligand. 6 neutral ligands bonding to chromium. And the overall charge of the complex ion is 3 positive, implying that the positive 3 is from chromium itself. So the chromium in this complex is charged positive 3. So we need now to draw the orbital diagrams of the metal itself. The ligands, we are not concerned for now. We are concerned with the metal, okay? So what happens? How do we draw the orbital diagrams of a metal? We must first of all start with the electron configuration of chromium. If you go in the periodic table, which we've already learned, how to assign a metal, whether it is D1, D2, D3, or D4, what do we find? Let's go and see. So let's just scroll to the summarized periodic table and identify where chromium is. So if we use this periodic table, which now you'll be using commonly, we look for chromium, it's here. It is a D4. This is D1, D2, D3, it's a D4. So what does D4 means? It is D4 S2, which can be rewritten to D5 S1, okay? And that is exactly what you find here, okay? That is exactly what we find in this slide that we had reached, okay? Okay, so that is exactly what we have here. It is a D6, a D4, so it is S2, and therefore it is D5 S1, and that's what exactly we have there. Now, you need to form the ion. So already you've drawn it there. Okay, once you draw it, this is what you'll get. Because you start with the D orbitals. D orbitals are usually 5. Okay, then you fill in 5 electrons because it's D5. Then S1 follows. Then P follows in that order. D, S, P. Okay, of course, this is 3, 4, 4. Then once we're at that point, we now do the loss of electrons. So first of all, you lose that one, then the other two, so that you lose a total of 3. All of us know very well if it's a metal +3, it has lost 3 electrons. So we end up with this configuration and orbital diagram for the metal ion. So once we are there, now we can represent our metal ion and see other things that apply to it later, shortly. Another thing we need to remember is bonding. What happens during bonding? During bonding, when you have a covalent bond, there is equal sharing. Give one, then you pair. That is equal sharing, and that is a perfect covalent bond. But we have another bond whereby one gives everything, and that we call coordinate bonds or coordinate bonds or dative bonds. And these are the bonds we find in metal complexes. Okay, so in metal complexes, we find such bonds, and we can already speculate here that this complex that we are concerned with for now contains coordinate or dative bonds. And that's why such complexes are called coordinate complexes, because of the type of bonds in them. Okay, so in such a case, what do we see? We see that in this case, chromium does not give anything to bond to those metals, to those ligands. Chromium does not contribute anything to bond to the 6 amine ligands. And the bond between the 6 amine ligands and chromium is coordinate bonding. So what does that mean? It means basically chromium stays like this in that complex. Its electrons are never affected. These 3 electrons remain the way they are. Okay. Then the ligands will just bring their lone pairs in the empty orbitals. Okay. So there are 6 of them. So they'll bring here 2, opposite direction, another 2 there, opposite direction, another 2, another 2, another 2, another 2. So that you find one NH3 will put there its electrons, another NH3 will put there its electrons, another NH3, another NH3, until you have all the 6 entering their electrons in those empty metal orbitals. And that is now represented here. Okay, so if you look at this slide, you can see all the steps that have been followed to explain coordinate bonding in a metal complex using what we call the valence bond theory, VBT. So it's so clear how bonding has happened between the metal complex and the 6 amine ligands. So this is the neutral one, then this is our chromium ion, and that is the ion that bonds to the ligands. And how do the ligands bond? They put electrons in the empty orbitals of the metal. So it will put in these empty orbitals, which I'll circle. And it only needs 6 of them because there are 6 ligands. And that is what I've just said. Each amine brings in the lone pair, and each amine has NH3 with 2 lone pairs on nitrogen, and those are the lone pairs that enter there. And there are 6 of them. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So we go to the crystal field theory, explain bonding and magnetic character of complexes. VBT fails to, VBT succeeds, okay, to explain bonding and magnetic characteristics of complexes. So we can clearly say that this complex is paramagnetic. Why? Because of the unpaired electrons. So it is paramagnetic. Unpaired electrons, so it is paramagnetic. And when I started, I said clearly that experimentally, this complex has been found to be paramagnetic. So it is not news, it is the truth experimentally as well as theoretically. So that's why we are saying that VBT is very good in explaining bonding as well as magnetic characteristics of a complex. But what does VBT fail to do? It doesn't tell us about color and other issues, quantitative dimensions. So we have a new theory called the CFT, which explains where VBT failed. So what is CFT? Is a model of electronic structure of transition metal complexes that considers how the energies of the d orbitals of a metal are affected by the electric field of ligands. So ligands affect energy levels of d orbitals. So ordinarily we assume that the d orbitals are at the same level, energy level like that. But in reality they aren't, they actually split. Okay. So CFT assumes that ligands are charged, okay, and it assumes what we call anionic ligands having a negative charge, whereas neutral ligands like ammonia having a negative charge because of the lone pairs. So either way, it is assuming that ligands must have a charge on them. So another key thing here we are seeing is that ligands don't have a positive charge. Ligands ordinarily have a negative charge, either as anions like chlorine or as neutral ligands like ammonia. So before bonding to a ligand, all the 5d orbitals in the metal are of equal energy, but after bonding, they take up different energy levels. And let's see what happens. So first of all, I will take you to I'll take you to the shapes of the orbitals. So this is not for cramming, it's just for helping us understand. So don't cram this because it won't help much. You'll just strain your brain for no good reason. But you need to understand how this came up so that when we go to the application, it's very easy for you to follow. So we have 2, 3, 5 types of orbitals, d orbitals, and each of them has different shapes. Okay. Now we have the first type, which is a dz squared. It is oriented along the vertical axis, the z axis, and this is how it looks. Then we have the other one, which is oriented on the x and z, x and y axis directly, okay? And that is what it is. Then we have another three that their orientation is not directed to those axes. Their orientation happens between the axes, okay? Like this one is between the axis, between the axis, between the axis, between and between, and so on. If you look at these three, they're not oriented directly with the axis. Now let's go to the CFT. What does it tell us? Ligands are what? Negatively charged. And ordinarily these ligands will occupy spaces that are directly oriented to the XYZ axis. Okay. So when a ligand comes in, it will be directly oriented to the x-axis. When a ligand comes, It will be directly oriented to the z-axis like we are seeing in the first case here. It will be oriented directly there. Then it will cause this. So there's a ligand here and there's a ligand there, oriented directly where I've circled. So remember, the negative charge represents your ligand. Okay, the negative charge represents your ligand. Just a minute, I need to minimize my WhatsApp. It's popping up onto the screen, so that is a real disturbance for me as well. So just a small stop so that I can do away with it. So sorry for the inconvenience. So we have pop-ups from my WhatsApp coming up. I may not get time to get rid of them for now because I have to get this record finished. So what is most important is this. So just neglect them. If they show up on the screen, just neglect them. So I want us to look at this case. So when ligands come, okay, I want us just to get this before we go into this explanation. When ligands come and bond to a metal, it is assumed that a metal can bond up to 6 ligands, and those ligands will occupy the 4 spaces, then the 5 spaces, okay? So we have something like a vertical, a horizontal plane, which has one ligand, another ligand, another ligand, another ligand. Then we have another one up, another one down, okay, like that. And ligands, let me use a different color again. And ligands along that axis is your X, okay? Ligands along that axis is your what? Y, okay? And ligands along that vertical axis is your Z. And what else are we assuming? Each ligand is a negative charge. Having explained that, then what does it mean? Now let us apply it in the CFT. So in the CFT, we have 4 types of orbitals orienting themselves differently. There is this one that is oriented along the z-axis, this one along the x and y, and these other 3 are not oriented on the axis. Instead, they are oriented in between the axis, okay? So they actually don't orient themselves directly with the ligands. So those orbitals are not oriented directly with the ligands, okay? So when a ligand comes, it takes exactly the X, Y, Z orientation. And if an orbital is there, there'll be a direct interaction and therefore high repulsion and high energy. So the only orbitals that interact directly with ligands are which ones? This one, because it is oriented directly to the Z, and this d orbital because it is oriented directly to the X and Y. So these 2 orbitals will have a higher energy level than these other 2 orbitals, okay, than these other 3 orbitals, because these 3 other orbitals are not oriented directly with ligands, okay, and therefore they split. So that initially, we shall see how that splitting happens, so that initially, before bonding happens, okay, sorry for that. So that initially, before bonding happens, this is my metal ion, your chromium 3 plus. Before ligands come, then when ligands come in, we assume the energy drops. Remember that, the energy drops. Why? Your product and reactant. So your reactants will be at a higher energy level there, and your product will be at a lower energy level. So these are orbitals of our products and reactant, which is chromium. And the ligands coming in, you get your product, that is your complex. However, they don't remain all of them at the same energy level, they split, okay? The two that are oriented directly on the axis, those two. And the other three that are not oriented directly to the XYZ axis are there. And having done that, then we get to this point, whereby I've just told you, which I'll repeat, I've already told you what happens. Metals can bond to ligands, and the ligands bond in those four axes directly. Then those other 5, 6 axes directly. And the d orbital orients itself directly to that, while the other d orbital dxy orients itself to dxy. Let's see whether that is the correct orbital. Just a minute. Oh, that's a wrong orbital taken there. Okay, but if you look carefully, this one now is not oriented. Look at this one. It's not oriented to the there. So this orbital will not interact with that ligand, for example, because this ligand is on the Y, but this orbital is not on the Y, okay? So this is just a direct comparison of ligands that are aligned with the orbital and ligands that are not aligned to the orbital. So such an orbital that is not aligned directly to the X and Y will not be affected. Its energy will remain low. But this one that is oriented to an axis like that one directly in the path of a ligand will have a higher energy. So I think that's enough explanation. The rest you can always read by yourself. Now let's go to spins, high spin and low spin. What is a spin? So I'll redo what is a spin. A spin is just you add the summations of the orbitals such that an electron that is pointing upward, we give it negative a half, positive a half, and an electron that is pointing downward, we give it negative a half. So if those two are in the same orbital, okay, the total spin becomes 0, okay? So if we apply that concept in the ions we are seeing here on the atom, for example, the spin for this atom, neutral chromium, will be what? 1, 2, 3, 4, 5, 6. It will be 6 times a half, which will be what? 7/2. That will be the spin. 7/2. Okay. No, is it 7/2? No, it will be totally 3. Sorry for that. It will not be 7/2, but it will be 3. The total spin here will be 3. That is 1. 2 of them gives 1, another 2, 1, then those 3. So the spin for the neutral atom of chromium will be 3. Okay. What about the spin of the ion, chromium ion? The spin for the chromium ion, that one will be what? 1.5. Because that is 1, then a half, 1.5. Okay. However, in bonding, these spins can vary. High spin and low spin, we shall just see that shortly. So remember in Hund's rule, we just say you pair them up, you pair the lower energy first before you go to the higher energy levels. So if we look at this, but before we look up to that, I want us to know this, that when we are dealing with spins, we don't look at the ligands, we just look at the ion only, the metal ion only. So I'll want us to introduce one terminology before we go any further, and that is what we call the split. So the split is simply what we are seeing here, the energy difference between those two types of orbitals, the high energy orbitals and the low energy orbitals. And this energy difference is called the crystal field splitting. So it's the difference in the energy between the two sets of d orbitals on a central metal ion that arises from the interaction of orbitals with the charge or electric field of the ligands. So we move on. So if we now look specifically or directly on chromium ion, we look directly on that chromium ion. Okay, that's our chromium ion. If we look at it directly, what do we see? We see that these electrons will definitely occupy the low energy levels before they think of going to the upper energy levels. But all of them have already occupied and there's nothing extra to jump there. So it is already a low spin complex because there's no pairing possible here because the orbitals are free enough for everybody to get a room. If you examine any transition metal ion that has a configuration D4, D5, D6, D7, you'll find two bonding possibilities. So we want to see other complexes or other metal ions that have more than one possibility of bonding. For chromium, it's straightforward. This is the only way it can bond. It cannot jump up there, okay? Now let us see the ones that are more than D3. Okay, if it is D4, definitely you'll find others jumping there, okay? Or even you'll find pairing happening, okay? So let us see next. When can jumping happen or when can pairing happen? So it goes to what we call about spins so that we end up with what we call high spin and low spin complexes. When you do pairing, remember, when you pair up electrons, spins cancel, and therefore you are likely to get low spin complexes. But when you don't pair, spins do not cancel, and therefore you get what? High spin complexes. So a high spin complex is a complex in which there is minimum pairing of electrons in the d orbitals of the metal atom, whereas low spin is whereby there is more pairing, okay, in the d orbitals. Okay. So this is the periodic table, and I don't think if I need it now. I do not need it for now. So of course, we shall come to that later. So I want us now to look at ion, for example. So remember again, CFT theory just talks about the pairing and the non-pairing of electrons for the metal ion, okay? For the metal ion only. We don't talk about the ligands, okay? So let us look at this complex. This complex has neutral ligands. So these neutral ligands, we assume, are not affecting the electrons in the ion. So we just talk about the ion alone. Okay, so let us look at ion, the metal. Ion, the metal, Fe. So Fe is in which part of the periodic table? Fe is there. It is a D what? 1, 2, 3, 4, 5, 6. It's a D6. So it is D6S2. Okay, that is our Fe. So D6S2. That is what we have. Okay. And all of us know how to put electrons in the orbitals, and that is done for us. When it loses 2 electrons to form Fe2 or ion 2, what happens? These 2 will go. So this is the configuration of ion 2 in terms of the outermost orbital. So our concern is the outermost orbital. Don't worry about the innermost. The concern is the outermost orbital. That's why we go straight to the periodic table and say D1, D2, D whatever, okay? So no worries there. Everybody should be at the same page by now. Now, so how ligands occupy the metal orbitals is not our concern in this theory, okay? So now let us look at the two possible bonding here, or the possible arrangement of electrons in the orbitals, outer orbitals of the metal ion. First of all, these are our electrons, okay? So remember, first of all, the orbital split. That is the first thing we should remember. The orbital split, 1, 2, 3, because it's octahedral. Then 1, 2, okay? So that now we fill electrons in the lower ones before we fill in the upper ones. So we have how many in total? 1, 2, 3, 4, 5, 6. So we fill in the lower ones and it's full. So there's nothing in the upper ones. That is the first type of bonding we see in this metal complex, the first type of electron arrangement. However, we can still do what? We can just still fill, then jump, okay? We can fill, then jump. So we fill the lower ones, 1, 2, 3, then go up 5, 6. Then we start pairing from the bottom like that, okay? When we do that, what has happened? We jumped and went up here, okay? Before starting to pair, okay? In this case, we jumped up before pairing. So it was easy to jump up than to do pairing, okay? Here, we paired first everything before we thought of jumping. Of course, we didn't jump because we didn't have enough to take up there, okay? So when you do this, pairing before jumping, maximum pairing or all pairing before jumping, we get what we call a low spin complex. What is the spin of this complex? It will be 0. Half plus a half and minus a half, this gives 0, 0, 0. So the overall spin for that complex is 0. What about for this one? It will be a half plus a half, that is 1. This is 0, so this we have 1. Then this is a half and another half. So we have a total of 2 spins. So this is a high spin complex. So having gotten that far, we get those two possible bonding or electron arrangement possibilities. So we have those two possibilities, either high spin or low spin. High spins will be paramagnetic, whereas low spins are diamagnetic, and their spin is totally 0. So pairing energy. So we get two issues here: the split energy and the pairing energy. So there's energy required for pairing, which is called P, and energy for splitting, which is this gap. It's called delta. So we have scenarios where P is greater than delta. When the energy of pairing or the energy required to pair is more than energy required for jumping, then we jump. I'll repeat. If energy for pairing, okay, energy required to bring two electrons together is big, okay, then energy required for us to jump to a high energy level, okay, so what do? We take the route that has less energy. So you can see this is less energy and this is more. So we shall take the splitting route, and that is what we get here in case for the high speed when pairing is much, much greater than splitting. So this gap is very easier for us to jump, and that is the case. But the other way around for this one, the other way around for this one, okay, for that one, it's the other way around, and it is what? It means here that the P is less than the split, okay? So splitting, it means this gap for splitting is so big. So what do? We take the smaller energy option, which is what? Pairing, okay? So that's what it means. If P is less or P is greater than the split, what route do you take? And I've already explained to us. So I don't need to go much into the notes there. You can still read them for you on your own. So you would expect low spin diamagnetic ion 2 complexes to occur for ligands that bond strongly, okay? So they're just telling us we should expect ligands that bond strongly. What do? They cause you to form diamagnetic, okay? Low spin diamagnetic are which ones? The ones that you are pairing. When do they form? They form when ligands bond strongly to metals, okay? And when they bond strongly, they create a large delta, okay? So when they bond strongly, they create a large delta value, and they lead to low spin complexes. And that leads us to what we call spectrochemical series, which is an arrangement of ligands according to the relative magnitudes of crystal field splittings they induce. Okay, so the one that induces a bigger split is called a strongly bonding ligand. So if it's bond strongly, it induces a bigger split. Okay, and when it bonds weakly, the split is not weak. The split is not is small. So if I'm to represent, it means on this end, you have such a big gap so that there is more pairing, okay? The gap is huge, and therefore there is more pairing. Then on this other end, I can use a different color. On this other end, then we have the split is so small, okay? Like that. So the jumping is much easier, okay? So strongly bonding induce a huge gap, then weakly bonding induce a short gap. And what do you get? On this side, you get high spin complexes, and on this side, you get low spin complexes. And on this side, what do you get? More pairing, on this, less pairing. And of course, we have the middle one, which are just moderate, okay? So the moment you see a complex that is paramagnetic or has more magnetic properties, just know the ligands are bonded weakly. And because they're bonded weakly, electrons will just jump. They'll not pair up easily, okay? And the moment you see a diamagnetic element, or complex, it means the split is so huge and electrons have already paired up. That's why the spin is zero, and that's why it is less magnetic. And we can see that ionic species don't bond strongly. Ionic species don't bond strongly, but non-ionic species, the ones with the lone pairs, bond much strongly. Okay, you can see ionic charged, iodine, bromine, chlorine, fluorine, hydroxide. Neutral, water, sodium, ammonia, ethyl, amine, nitro, cyanide, and CO. Okay, the only charged ones are those ones, but majorly the negatively charged halogens are very weakly bonding. And that's why you'll find an ionic complex represented like that. Then outside there, you can have a chlorine, two chlorines. Okay, but these chlorines don't stick on the metal strongly, but the neutral ligands usually stick strongly on the metal. That's why we represent with that minus the anion on it. From this species, you can see that cyanide ion bonds more strongly than water, which explains why ion cyanide is a low complex spin and water is a high spin complex. Okay. You can also see why carbon monoxide might be expected to be poisonous. Okay. You You know that oxygen bonds reversibly to iron 2 atoms in hemoglobin. So the bonding is only moderate. So anytime you hear of something bonding reversibly, then it is a weak or moderate bonding. So it means all these bond reversibly, okay, easily, reversibly, while the other ones don't bond. These ones bond almost permanently, or what we call irreversibly. The ones on this side, reversibly, okay, they can bond and get off just like oxygen on hemoglobin ion. And now, if you bring something that bonds very strongly, like carbon monoxide, it will replace oxygen on hemoglobin and stick there permanently and therefore causing the poisoning, okay? Such that now carbon monoxide sticks there and oxygen cannot come back and stick there, and therefore you get to suffocate because your blood can no longer transport oxygen and only transports carbon monoxide. Of course, that is a very strong case during fire breakouts. So with that, having come that far, I want us to look at some more examples. And it brings us to us considering this complex, okay, cobalt 2 plus. So what is cobalt 2 plus? Again, for us to figure out whether it is both high spin and low spin complexes of cobalt 2 plus, it means we look for cobalt. What type of metal is it? Is it a D1, a D2, D3, or D5? So I'll scroll quickly to the periodic table and look for cobalt. Cobalt is here. So it is 1, 2, 3, 4, 5, 6, 7. It's a D7, S2. Okay. So we go straight to the question, and now we know it is a D7. We know cobalt is a D7 here. So we know cobalt is a D7. If we know cobalt is a D7, Just a minute, I'm having issues with power, so let me just get it stabilized, then we'll continue. So if cobalt is a D7, D7 is 2, and you form, what is the charge on cobalt there? Water is neutral, so the charge on cobalt is 2 plus. So it is cobalt 2, so it will lose that. Okay, so what do we remain with? We remain with just D7. So how does D7 look? So remember, CFT deals with only the d orbitals, okay? So it is 1, 2, 3, 4, 5, okay? 6, 7, okay? So this is what you start with, okay? So that is what you are starting with. Now, let us see how we can put in the splitting, okay? Remember, it's still a D6, okay, which is octahedral. And we have seen how octahedral orbitals split. How do they split? 1, 2, 3 down here, and 2 up there, okay? So we first of all say, what if it is a low spin? Okay, if it's a low spin, it means we pair up first. So we pair 1, 2, 3, 4. Oh, no. That's a mistake I've done. We do the usual rules that we learned in first year. 1, 2, 3. But now we pair because it is it is low spin. So we pair 5. That's 4, 5, 6, 7. So if we are considering that it's low spin, still there's something to jump up, okay? That is low spin, meaning that this gap delta is so huge, okay? Now, so that corresponds to what? It corresponds to what we can see there, low spin. Now, what about if it is a high spin? Remember, it is how many electrons in the d orbital? 7. So I'll rub this one so that we can get space. So there are still 7. So the same story again. We are assuming that it is high spin, okay? High spin means what? The gap is so tiny, so they can jump easily, okay? So it is 1, 2, 3, 4, 5. Why have I done that? Because the pairing energy is higher than the jumping energy. So the jumping energy that I've given it a new name is that split. Okay, that's the jumping energy is less. So they will just jump the moment you finished putting in each orbital before you start pairing. So those are 5. So that's 6, 7. Okay, and this is our high spin. What is the spin here? 1. And what is the spin up here? A half. Okay, so it means it is either way, the cobalt complex is paramagnetic. Okay, but it can form both low spin and high spin complexes. Now, having done that example, remember this is recorded, you can replay as many times and listen to it. Let us look at another example here. Nickel in water. Again, the same story again, okay? What is our story here? So what is our story here? Our story here is that again, we have nickel, which is different from cobalt. So again, the periodic table must be used. So we go to nickel. For nickel, what type of element is it? How many electrons does it have? So there we get, okay, nickel is here. Okay, nickel is there. It's a D what? 1, 2, 3, 4, 5, 6, 7, 8. It's a D8. So it's D8S2. So we note that D8S2 for nickel. So nickel is a D8. That's 2. And remember, nickel is a what? Is uh 2 positive. Just look at that. The charge is positive 2. So it means this one has been lost. So you have how many? You have 5 orbitals like that, and they have 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you now have to do the splitting. Okay, so you do the first consideration, low spin. Okay, low spin means the energy gap is so big. Okay, so you pair first, then you jump. So let's do 1, 2, 3. We don't jump because the energy gap is big. So 3, 4, 5, 6. Now we can jump because the orbitals are now full. So that's 6, 7, 8. Is that fine? Now, let's assume the other way around, whereby jumping is easier than pairing. Okay. When jumping is easier by pairing, what happens? Okay. The gap is tiny, like I've shown there. So jumping is easier than pairing. So it's 1, 2, 3, 4, 5, 6, 7, 8. The same story, okay? The same story again. So either way, it is forming a high spin complex whose spin is what? 1 in either case. The spin is 1, half plus a half, half plus a half. So it's positive half. Remember, all of them are facing up. So it's positive half plus positive half, which is 1 and 1 respectively. Now, I'll ask one question. What if you had a different ligand? Okay. If you had a different ligand, okay, then you'll expect a different type of complex. But let's jump to something else before we do that, okay? I'm just scrolling ahead just to know how many slides to go, okay? So I want us to do something to see something certainly different. We have only so far we've been looking at what we call octahedral complexes. Now I want us to look at square planar and tetrahedral complexes. All of us know what is a tetrahedral complex. A tetrahedral complex means if I have a metal like that, then it is just 4 like that. That is tetrahedral on the same plane. And you can see the splitting pattern in tetrahedral, how it looks like. Okay. So in octahedral, which we have already seen, the splitting is like this. That's how the splitting works in tetrahedral. Don't worry about the popping up of those WhatsApp messages. They're none of our business for now. Just, I can't take off time and deal with them. I have just to finish what I'm doing now for the recording. Now, this is what we've already seen for octahedral, okay? And this is now what we see for tetrahedral complexes, okay? Then we have square planar. Okay, sorry, I've made a mistake. Allow me to tetrahedral have also 4, but they look like that, like Tetra Pak. But square planar is what you get like that. Metal, then it's square planar like that. Everything is on the same plane. It's flat. So when it's square planar, this is how the splitting happens. Okay. And when it is tetrahedral, this is how the splitting happens. Okay. Then when it is octahedral, this is how the splitting happens. So it might be a bit, you can see tetra and octa are reversed. Okay. Tetra and octa are reversed. Okay. Inverse of each other. They're inverse of each other. And square planar is unique on its own. So maybe cramming all this can be a little bit terrible. So I think in terms of examination purposes, then I'll have to provide these splitting patterns. Then your work will just be to apply these splitting patterns to determine the magnetism of that compound and where it is, whether it is high spin or low spin. Again, we may not have to cram the spectral series, spectrochemical series, okay? We don't need to cram them. What we need to know is that what is the implication? If I have a nitro in my complex, then I change that nitro and put there bromo. What is the effect on the split? Okay? What is the effect on the split? And that effect goes down to affect what? The 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 pattern, whether magnetism or non-magnetism, diamagnetic or paramagnetism. And this, what I'm teaching now, will be the story for our Cat 2, which I'll be sending shortly. I'll be sending that shortly. So this will be the story for our Cat 2. So we look at a problem here and see whether we can sort it. Describe the bonding in a 4-coordinate complex, that is square planar or tetrahedral. So a 4-coordinate complex can be either our square planar, which is like that. That is a 4-coordinate complex, or tetrahedral, which looks like that. Okay, the two are both 4-coordinate complexes. So they can have either the tetrahedral split, which is the reverse of octahedral like that, or the other square planar splitting, which is shown here. So we go to the story and see what happens. So you are dealing with a square 4-coordinate complex called nickel cyanide. Okay. So describe the d electron distributions of the complexes of nickel with ammonia and nickel with cyanide according to the crystal field theory. We are told the tetraamine is paramagnetic. Tetraamine is paramagnetic. This one is paramagnetic, meaning that there is no doubling in it. There must be some electrons that are not doubled. Then we are told the tetranickelato is diamagnetic, this one, meaning everything is paired up, okay? So it means now we have to see which one is likely to give us non-pairing, which is diamagnetic, and which one is likely to give us pairing up. Pairing up means dia, two, pairing up. So which one is likely to give us pairing? It should be this type of splitting. And whereas this type of splitting is not likely to give us pairing because there's some space. Okay. So you can actually sort this question easily by, you can sort out this question easily by, first of all, considering one at a time. Okay, remember there are 4-coordinate complex. So it means I can look at this nickel when it is tetrahedral and when it is square and see what happens. Then I can also consider that when it is tetrahedral and when it is square. Then I see which one is which, okay? So I will take time on that because the answer here is more direct, but the reasoning is a bit complicated, okay? So maybe we need to prove it one at a time. So what shall we do? We shall start with the tetraamine group. So I'll do tetraamine. First of all, I'll do it with, I assume it is square planar. Okay, I assume it is square planar. Then what is nickel? Of course, I have to look for nickel, and I'll find that nickel is which type of metal. So again, I must scroll to the periodic table. So it is a matter of using the periodic table throughout. You can't do without it. Nickel is 1, 2, 3, 4, 5, 6, 7, 8. So it's a D8. Nickel is D8. So having known that nickel is D8, let's scroll quickly to our question. So nickel is D8. D8, S2. But we can see from this, we can see from here, it's +2. Remember, ammonia is neutral, okay? So we can see clearly that nickel there is +2, okay? So that 2 has disappeared. So remember what I'm dealing with, I'm only dealing with this first complex, first of all, okay? So it's a D8. So if I assume it is square planar, whose split looks like that, okay? Then let me start the work. So I'll do 1, 2, 3, 4. I'll put the down ones first because remember going up means I have to start. When I go up again, it means, but in this case, remember the two ligands we are dealing with are bond strongly, okay? Meaning if they bond strongly, then we get paramagnetic and uh, we get high splits or high deltas. When they're bonding strongly, the delta is high, so pairing becomes a priority, okay? So I'll pair there, then pair here, that is 6, okay? Then 7, then 8. And we are told it is what? Paramagnetic. So in other words, it is not this type. It is not that type. It's not planar. Okay, so it must be tetrahedral in shape. And so if I do now this ligand, this complex, if I do that complex, assuming that it's tetrahedral, I'll get this structure. Why? I'll still start with 8 down here, pair, then go up here and add, then I'll get it like that. So remember our ligands are high spin, not high spin, but low spin ligands because the delta is so huge from the spectrochemical series. And again, if you have forgotten, you just go back to your spectrochemical series and refer, okay? These are your spectrochemical series, and we are dealing with what? We are dealing with ammonia and cyanide. And you can see the increasing in split. So their split here is so high that pairing will happen before anything else happens, okay? So that is something that we have to put in mind. You have to learn to think using as much data as possible. Now, having done that, I go to the other complex, which is what? Cyanide, okay? and see which is the structure of the cyanide. Because what? From data, the cyanide one, this one is what? Diamagnetic. There is lots of pairing there. It is diamagnetic, and at the end of the day, there is no unpaired what? There is no unpaired electron. Every electron is paired up. That's why it is diamagnetic. So anytime you hear diamagnetic, just know all electrons are paired up. Okay. So let us again do the same story. It is still a 4-coordinate complex, as clear as that. And we either expect tetrahedral splitting or square planar splitting. So again, I can start with square planar splitting. So remember, it is D8 S2. Okay. What is the nickel charge? Cyanide is -1. Okay. If you have 4 cyanides, they should give us -4. But the overall charge there is -2. So we can calculate the charge of nickel. Okay, and again, we know how to calculate charges of metals. If we know the ones we know and the ones we don't know. So we don't know for nickel, we can call it X, okay? X plus the one of cyanide, 4 cyanides, that is -4. Then the overall is -2 is equals to -2. So what will be the answer? The answer is definitely +2 for the nickel. So our nickel is +2, as simple as that. So having established that our nickel is +2, and we know that nickel is D8 is 2, then it means that this is lost, so we still have D8. And then the same story, we assume it is tetrahedral. Okay. No, square planar first. We start with square planar, okay? Then we find whether they'll be pairing or not. So if it's square planar, what happens? The same story again, 1, okay? 2, 3, 4, okay, 5, 6, 5, 6, 7, 8. So it is square planar. This corresponds exactly with it being diamagnetic, okay? Nothing is unpaired. Everything is paired, and therefore it is diamagnetic, and therefore it is this one. Okay. So it's about pairing and not pairing. Because if we will do the same ion, remember, is the one that we are using through. So if we do for this, the nickel is everything here. Remember, there is nickel being used here, nickel 2+, nickel 2+ there, and also nickel 2+ here. Remember, you can also draw your charges like that to mean 2+, okay? So you have nickel 2+ here, and also you have nickel 2+ there. We are dealing with the same ion, only that we need to establish whether this ion is paramagnetic or diamagnetic. And if it's diamagnetic in this complex, this is how it looks like. And it is paramagnetic in this complex, this is how it looks like. So again, the ball is in your court. You revise it and look at it in details at your own free time. So now we will let you get free time and look at this complex, and you are told it is tetrahedral. Okay, you are told it has a tetrahedral geometry, and assume it is a high spin complex. Assume a high spin complex. Okay, unfortunately, that is not what we expect, unfortunately. Why? Because in the spectrochemical series, we are expecting chlorine to be somewhere else. See where chlorine is. But we have been told chlorine ordinarily will give you low spin because this is small. The split is small here. So this question is even more simplified, actually. If you look at it, it's already simplified for you. I've already told you it's tetrahedral. How is the tetrahedral split happening? Tetrahedral split happens just like that, very simple like that, 5. Then you are told it's high spin, so you have to describe how the electrons are arranged. And you are told to assume it is high spin. So high spin means you don't pair. Okay, that's what we are being told. Don't pair it up. It's assumed that these split energies are huge. Of course, we have already been told to assume that. Okay, so it is cobalt. So we need to find out its cobalt and how does cobalt look like. And definitely we need to know whether it is a D1, D2, D3, and so on. So we quickly scroll to the periodic table and look for cobalt. And here is cobalt. 1, 2, 3, 4, 5, 6, 7. So it's a D7. So we quickly go to that. Already know that it's now D7. So it is D7 S2. So we can easily calculate the charge on cobalt. We know how to calculate it. And if you calculate it, you'll get it's +2. It's just a coincidence that we are getting ligands with +2 metals. It doesn't mean that all ligands will have +2 metals. No. You calculate that if cobalt is X, chlorine is 4 of them, -4. Then the overall charge is -2. So cobalt will be +2. Okay. So that is lost. So we have D7. So we start D7 and it's tetrahedral, and that is the split of tetrahedral. No. Let's see tetrahedral. Tetrahedral splits. Okay. A is tetrahedral. So tetrahedral is so that is tetrahedral, and this is square planar. So it's tetrahedral. So that is the split we are expecting. So we go straight to that tetrahedral. So tetrahedral is the reverse of octahedral. Okay. So tetrahedral is the reverse of octahedral. So that is our tetrahedral, and there are 7. So it is 1, and we are told it is high spin. So no pairing. Pairing is minimal. So we can jump immediately. So that's 1, 2, 3, 4, 5, then 6, 7. So that is the arrangement, and overall the spin is 1.5. So that is it for now. What I'll go next to. So you learn more of these splits when you do organometallic chemistry or when you do complexes or coordinate chemistry. So that's just an introduction because we are learning about transition metals and we need to know all this about transition metals. So next and lastly, we look at color, okay, which is UV-Vis. When you talk about color, you're actually talking about UV-Vis spectroscopy. Colored compounds absorb certain wavelength in the UV-Vis range, and whatever is absorbed is transmitted as color. So you absorb something and another one goes out as color. So I will quickly reintroduce you to Roy G. Beeve. So if something absorbs high wavelength, the color will be this one. So this is absorbed and this is seen or by your naked eyes. So what is absorbed is not seen by your naked eyes. What is not absorbed is what your naked eyes will see. So I've said if something is absorbing in the short wavelength, like it is absorbing this wavelength of colors, then this is what will be seen. So if something is absorbing blue, its color is red. And vice versa. If something is absorbing red, its color is blue. So many transition metals are colored. Why? Because of transition of electrons from d orbitals in the lower energy level to d orbitals in the higher energy levels. And again, this can be explained in terms of CFT. So for example, this compound here, it absorbs in this range. That is its maximum absorbance. Okay. So titanium, this titanium is a D, is actually a D2. Titanium is a D2. Okay. And S0. So when it becomes titanium +1, it loses one electron. Actually, sorry for that. Titanium is D. Okay, maybe I'll just take you back to the periodic table so that you see what the titanium is made up of before we make any conclusions. So where is our periodic table? Periodic table is nowhere to be found. It is here. So this is our titanium. It's a D2, meaning it's D2S2. And in that question of titanium, we're dealing with is titanium 3 plus, okay? So titanium 3 plus has lost those two and one of that. So titanium 3 plus is basically a D1, okay? After losing those 3 electrons. And that's why you can see in that orbital diagram that we had already started looking at, it has only one electron, okay? That's why it is just one electron here. So when you supply energy, what happens? That electron jumps up there, and that causes color to be absorbed. So that electron jumps, and that electron is using energy, and that energy is equal to the energy absorbed. And what is not absorbed is the remaining in form of color. So remember, what is light? Right, light is Roy G. Biv. Okay, then different elements, different ions will pick a specific part of the Roy G. Biv and absorb it. Then the remaining part forms its color. So when we look at this diagram, Roy G. Biv is written in reverse. Roy G. Biv in reverse, like that. And you can see the blue is on this end and the red on that end, okay? And we know that from first year that the blue zone is high energy and therefore shorter wavelength, and we can see that clearly. And the red side is low energy and long wavelength, okay? So what we are seeing is here is that our complex is absorbing strongly in the yellow green region. And whatever is unabsorbed is a combination of red and blue, and it gives that magenta color. And we are told the crystal splitting, that is delta, consequently can be related to the light in this equation. Okay, and we can look at it like that this gap is related to light, and that gap is inverse to the wavelength. Okay, so that if the gap is huge, like that, what does it mean? For you to jump, you need lots of energy. And who will provide you lots of energy? Shorter wavelength will give you lots of energy than longer wavelength. So what does that mean? If this is long, the energy wavelength should be short. That's why we're talking about the inversibility like that. Okay. So that ligands that create a bigger split, will cause absorption of high energy wavelength, and therefore your complex will be reddish in color. So if I have a ligand that creates a bigger split, like we saw there, the ones that create a bigger split. Let's see the ones that create bigger splits for those who are forgotten. Which ones are causing bigger splits? Water, cyanide, and so on. Okay, so see the ligands that are causing bigger splits. Here they are. So these are causing bigger splits. Remember, increasing split like that. So this cause bigger split. And when they cause bigger split, what do they cause? Absorption of short wavelength. And when you absorb short wavelength, it means you are absorbing the blue color. And if you are absorbing the blue color, it means my complex will be red in color. So remember, it is the Roy-G-Biv thing again. If I absorb blue on this end, what remains is red, and therefore my complex will be reddish. So in other words, if you get reddish complexes, there's a high possibility that these reddish complexes are containing ligands that cause higher splits or large splits, and these large splits cause us to absorb high energy radiation. What is our high energy radiation? The blue region, which is GIV, which is BIV, that is Roy-G-Biv, BIV. So it causes us to absorb the BIV region. And if we are absorbing the BIV region, what remains is the red region, and therefore the complex will be red. The other way around, if you have complexes that contain these ligands I'm circling, these ones cause shorter splits or very short splits. And when you have a short split, you don't need a lot of energy to cause electrons to jump, okay? So if you have a shorter split like that, what happens? You need very little energy, and therefore you'll absorb long wavelength, which is red. And if you absorb the red, if I absorb the weaker, then what remains is the blue. Okay, so what does it mean? Ligands, complexes with these ligands, weak bonding ligands, will always be blue in color. Okay, I think that's enough explanation. The rest is on your part. You do the remaining part, and I think the rest you can read on your own. And this table actually summarizes everything, provided we know what are the principle guiding everything. Roy G. Biv. This is short wavelength, which means high energy on this end. And the other end is long wavelength, low energy. Okay. And if you absorb this side, this one is remaining, and that is your color. So the same story is here. If you absorb violet, okay, if I absorb violet, which means I'm absorbing this end, what color remains? Yellow-green. Okay, and when I absorb red, let's go down. If I absorb red, which color remains? Blue-green. Okay, if you absorb that, blue-green remains. And that is the crux of this table. Okay, so again, it's up to you to read on. So I've come to the end of this session, and At the end of this session, I have expectations from you. And one expectation is that if I change ligands in a complex, can you predict the color change? If I give you the magnetic property of a complex, can we explain how the electrons are arranged or distributed? That is specifically the d orbitals. And that is it. So we can call it a day. Goodbye.